discuss this really very active topic in detail today. And we have 8 speakers, and then afterwards we'll have an hour discussion panel at the end. We'll talk about the rubric of that when the time comes. In the first instance, our goal here is to identify areas and problems of quantum chemistry, or computational chemistry, for which quantum computers could show an advantage. And there's a lot of debate about this, so we've assembled 8 experts who are working in this area to present candidate systems and their perspective. And so we'll start with Ivan Kassal from University of Sydney, talking about chemical dynamics on quantum computers.
Hello, thank you so much, Brigitte, and thank you for the invitation for coming here, and thank you to all of you for coming. So I'll talk about chemical dynamics. And I want to start by saying that most work so far, and I think most of what we'll hear about in the rest of the day, will be about electronic structure. And I think in terms of identifying opportunities for quantum advantage, I want to try to convince you that dynamics is another big opportunity. And I'll talk about 2 things. One is about analog simulation of chemical dynamics. And we've developed ways of doing that using vibrations of trapped ions to simulate vibrations of molecules, so using bosons as an additional resource, which allows us to get resource efficiencies that are 1,000,000 or 1,000,000,000 times higher than what you can do with qubits. And I'll show you outlines of a few experiments. But the main part of my talk will be a more recent digital simulation algorithm, which is end-to-end. So it's full dynamics of molecules, so nuclei and electrons on a grid in first quantization. And the advantage of that is that it's bounded and all the errors are controlled. So we can actually say exactly how much it's going to cost all the way down to individual gates. So if you look at the covers of glossy magazines where chemistry and quantum computing have appeared, it sort of started in 2010. And then, chemical potential is not a quantum thing, but anyway, and so on, chemistry by qubit. All of these are experiments that involved electronic structure on digital quantum computers. And so if I could kind of summarize chemistry and quantum computers, I could come up with a little grid like this, where, like I said, most of it is digital. Digital, I mean just qubits and gates, the normal framework of quantum computing that you'll find in the textbooks, and the static problem of electronic structure. This is where the vast majority of it has been done since Alana Spurguzic's paper in 2005. And there have been small experimental demos, including the ones I mentioned on the previous slide. You can also do electronic structure on analog computers, and by analog I mean a system which is not a universal quantum computer, but one that you can have the same Hamiltonian as the system that you want. And there's been very few theory papers here, and they've kind of been scattered, and there's been no experiments that I'm aware of. And then today I'll talk about the second row, which is dynamics. Both digital, this is work that started back when dinosaurs roamed the earth, and so when I was a PhD student, and has not been experimentally demonstrated yet. And also, so more recently, I've been interested in doing analog simulations as a way of bringing some of that quantum advantage, if you will, forward. And so I'll mention that as well. And the reason for studying chemical dynamics is not to say that electronic structure is not interesting, but that, in a sense, for me, it always seems weird when you take quantum chemistry, and we write down for the students the time-dependent Schrodinger equation, and then we drop the time dependence like a hot potato, and then everything else is just stationary states, which is really weird for the science of change to be done in terms of stationary states. So dynamics tells you everything about chemistry, reactivity, spectroscopy, everything else. It's unitary, which is very convenient if you want to put it on a quantum computer, and it's therefore provably efficient. So you can prove that these algorithms scale linearly, quadratically, cubically with system size, which you can't do for electronic structure. That, in the worst case, is QMA hard. And the separation between what can be done on quantum computers and classical computers is very large, or I would say probably larger than what you can do classically, than you can do in electronic structure. So the gold standard method for fully quantum chemical dynamics is multi-configurational time-dependent Hartree, which in the worst case scales exponentially badly. So I'll give you 2 snapshots from the bottom row. And first I'll start with the analog approach, which we've worked on since for the past 5 years. And this is a collaboration between my group, and the experiments are done by Professor Tingray Tan, who's my colleague in the physics department at Sydney Uni. And analog simulation has been around for a long time. This is from the 17th century. Right? You turn a handle in the back, and it makes the planets turn. And this is much more, more accurate and more a faster calculation than the alternative at the time, which would have been slide rules. And we've asked the same question of, can you do that for simulating chemical dynamics? And the answer is you can. And so to kind of frame the problem is, in fact, for the rest of this talk, will be that non-adiabatic dynamics is particularly hard on classical computers. So adiabatic dynamics means that everything is on the same potential energy surface. That's what you, and that's where you have the relatively simple, well-developed chemical intuition that we teach in organic chemistry. And in organic chemistry, you have diagrams like this: reactants, products with a transition state, and this is labeled as the reaction coordinate. God knows what that means. Well, what it really means is that you have a high-dimensional surface in the space of nuclear coordinates. At every point in that space, you solve the electronic structure problem, and then you connect the reactant well with the product well with the path through the mountains, as it were. This gets much harder when you have non-adiabatic dynamics, so you have multiple potential energy surfaces, and you can end up with entanglement. So you have a failure of the Born-Oppenheimer approximation, especially at conical intersections, which is where the Born-Oppenheimer approximation breaks down fully. And you can have, for example, a wave packet that's sliding down the top surface, branching into different ways, and you might be interested in knowing what is the ratio of the wave packet staying on one surface or the other. And this happens all over photochemistry. Everyone's favorite example is retinal. This is what happens in your eyeball. This is how you see. The molecule has a cis bond here when a photon comes and switches into a trans bond. And the way it does that is through a conical intersection. So I have ground and excited surfaces. Isomer A is cis, isomer B is trans. The wave packet initially in the ground state is excited to the excited surface, and then slides down through the conical intersection and down back onto the ground state surface in the other isomer. And it's a very difficult problem because it involves both nuclear and electronic motion. And it could have been otherwise. Why did the wave packet go through? Why didn't it reflect off of the intersection? That sort of thing. So this particular example is extremely efficient, and it's not exactly possible to simulate it accurately. So to do this on an analog simulator, we've proposed to do it on ion traps. So trapped ions, they're held in vacuum by electrodes, and you can address them with lasers. And the basic idea is to use bosons as a resource for calculation. So you have normal modes of vibration of the ions. These are used, for example, if you want to use ions as a digital quantum computer, you use the vibrations as a bus to implement a C0 gate, but we're using them here directly to store the quantum information about the vibrations in the molecule. So here, for example, a vibrational mode of water. And the way this mapping works, here's an example on pyrazine, which is like the hydrogen atom of this field. You can construct the adiabatic surfaces by doing electronic structure at every point, and then you connect these, and then you do a diabatization procedure, which gives you diabatic surfaces which are coupled. And for small displacements, the diabatic surfaces are quadratic, but of course you can then put in higher order corrections. And the basic idea is that then you want to match the Hamiltonian of your molecule to the Hamiltonian of your simulator. So for pyrazine, in a two-state, two-mode approach, so you have two electronic states and two vibrational modes. So here I have two vibrational modes, here I have two electronic states, and I have a vibronic coupling between them. That's the coupling between the electronic states and the modes. And these different parameters come from the surfaces. Whereas on a single trapped ion, it has internal states, which you can use as a qubit. That's shown here in orange. We're just using two different vibrational modes. So it's translation in two directions into trapping potential. And again, you can have state-dependent forces which are induced by lasers. And the point here is that this is programmable in the sense that you can tune every one of these parameters in the simulator independently by tuning the intensities of the lasers or the detunings of the lasers. So you can reproduce any two-state, two-mode Hamiltonian with just a single qubit trapped in two directions. And then the idea, like in every sort of quantum simulation, is you need to initialize it somehow. This involves, in this particular case, a displacement of one of the bosons. Then you have time evolution, and that's what's easy in analog simulation, is that you just let it evolve under the Hamiltonian that you've induced in your simulator, and then you make some measurement at the end. And we've done a series of experiments, and I'll highlight two. This one is a demonstration of geometric phase interference in dynamics around the conical intersection. So even if you're entirely in the ground state, so this is a Jahn-Teller Hamiltonian in 2 degrees of freedom and 2 states. So there's a conical intersection here, but my wave packet is on the ground state surface, and it stays entirely on the ground state surface, but it goes around the conical intersection. And it turns out that when you do that, you acquire a Berry phase, or geometric phase, which means that at some point later, where you would think that the wave packet would go around and constructively interfere on the other side, it interferes with itself destructively. So you end up with a node on the other side. And this was done by my colleagues in their ion trap. This here is the measured wave function of the ion, the initial state, and the final state at this point in time, where you can clearly see the interference. To show you that it's programmable, we published another paper last year. So like I said, for example, these are the surfaces for pyrazine. But the difference between other molecules that can be represented as two-state, two-mode systems is just that they have different parameters for these two-state, two-mode systems. So the different frequencies and energy splittings are different. And so here are the results. And so for allene, butatrine, and pyrazine, the surfaces are different depending on where the conical intersection is, whether it's symmetric or not. And again, you can see the plots on the bottom show the probability of remaining in the top diabatic state as a function of time. And you can see the dynamics is quite different, but it's reproduced well by the simulator. The other thing that's shown here at the end is that we can use the noise that's present in the simulator to simulate open systems, or we can inject additional noise into the system to simulate what would happen if this was a molecule in an environment. So in blue is pyrazine in a simulation of pyrazine in vacuum, and then in orange and red, we're increasing the strength of the coupling to the environment. And I think this is a particular opportunity for quantum simulation of chemistry, because most of the chemistry we do is in open systems. It's very rare that we care about molecules in vacuum. But open system simulations are much harder to do on classical computers because you need to worry about density matrices and so on. Whereas on an analog simulator, it's easier. It's much easier when you tell experimentalists that you need them to do a bad experiment than when you tell them that they need to eliminate all noise. And the slide I want to end on is to talk about there's an enormous improvement in resource efficiency in doing this. So you could say, so we're calling this mixed qubit boson simulation, and we calculated how many qubits and how many gates, what memory and how many quantum degrees of freedom and how many gates you would need to simulate this on a qubit-only quantum computer. And in terms of memory, so you have 2 degrees of you have 1 qubit. That's one. You need 1 qubit to do that. But to simulate the continuous motion along the 2 coordinates, you need at least 5 qubits along each direction to be good enough. So the number of qubits is about 11. If you want to simulate an open system, it's even more. But where the real kicker is in terms of the number of gates. If you're trying to discretize a continuous degree of freedom into qubits, then you start getting these different types of complicated calculations that you have to do. And so what really is just one compound laser pulse in an analog simulator ends up requiring 100,000 gates, 100,000 perfect error-corrected logical entangling gates. And for the example that I showed you where it's an open system, where you're simply implementing it coupled to the environment, that requires another factor of 3 orders of magnitude. So the advantage in terms of the volume of the system that you're simulating is about 6 or 9 orders of magnitude. So the simulations that we've already done would have required 1 million or 1 billion perfect logical gates on a quantum computer, which I think is quite impressive for what my colleagues can do in their ion trap. So how do you generalize this? Well, can we have additional states and additional modes? Yes. You can use straterization, or you don't actually need to. You can simulate whatever chemically interesting observables you want. We have written papers about simulating spectroscopy. Any type of spectroscopy can be done with this, like higher order spectroscopy, magnetic spectroscopy, the rest of it. Rates of chemical reactions, branching ratios, all can be measured efficiently. In terms of anharmonicities or higher order couplings, we have a way of doing that. And that has been demonstrated experimentally as well. And for open systems, again, we have different ways of injecting noise. If I'm simulating a solvent where electronic dephasing is more important than vibrational dephasing or vice versa, I can just inject different types of controlled noise to do this. Of course, there's many challenges here. One is that it requires parametrized surfaces, like any kind of classical, like if you have MCTDH, you need to have the surface to begin with, and in some cases that classical calculation will end up being difficult. We don't yet know how to handle dissociative surfaces because we're expanding it, for example, in Fourier series to get the higher order terms, so that's not very good for getting a dissociation. And there's a question of error reduction, like any type of analog simulation, classical or quantum. It can be useful, but it's not going to be infinitely scalable. And so the question is, how do you reduce the noise to a level where it becomes practically useful in the same way that the planets moving around the sun was useful at that time? Okay, and so then in the second half of my talk, I want to talk about doing digital dynamics. So this now, assuming you have a digital quantum computer. And so this was done by my students and postdocs over here, including Patrick, who's right here, and our collaborators, Bill Huggins, who I think might also be here. I think, or at least he was on the, hello, and Guang Hao and Dominic Berry. And the concrete example that I want to focus on is photodissociation, because this is a particularly difficult problem for classical computers, and even for the analog simulation that I showed you just a moment ago, we don't know how to do photodissociation that way. And the idea there is you need to prepare an initial state which corresponds to some molecule having been excited. Then you evolve it in time, and you get, this is meant to be a superposition of these two possible channels. You get some kind of complicated wave function. And then you make a measurement of an observable, which, for example, will again be a branching ratio. So in this case, it might be there's a 20% chance that this hydrogen falls off. That hydrogen used to be connected to the oxygen, or it might be that this hydrogen, which is connected to the carbon, falls off. Okay? And this is, like I said, a very difficult computational problem, because you have a very high-dimensional Hilbert space. And so what do we want in a algorithm like this? Well, the algorithm that I'll tell you about has all of these properties. It's a fully dynamical simulation, so it uses the exact molecular Hamiltonian. We're not making approximations like the Born-Oppenheimer approximations or truncating surfaces to second or fourth or sixth order. It's end-to-end. We provide explicit circuits all the way for initialization, propagation, and measurement. It's efficient, so it's polynomial in molecule size, the duration of the simulation, and the error. And the errors are bounded and they're controlled. So we can calculate the different, we can bound the error between the true and the computed observables, such as yields. And these are all systematically improvable. So we want to drive the error down, we just increase the fineness of the grid or whatever. And the idea of doing chemistry on quantum or dynamics on quantum computer goes back to 2008. So and so this Peter was one of my co-authors, and when I was a PhD student in Alain's group. And the basic idea is that when I said doing full dynamics and everything is exact, what I mean is that chemistry at the bottom is really just a Coulomb interaction. You have this is a molecule of water. You have 3 nuclei, and you have 10, I think, 10 electrons. And they're all interacting under the Coulomb potential. Well, there's the Hamiltonian includes the momentum of all the particles, the kinetic energies, and the only potential is the Coulomb interaction. And Coulomb interactions are diagonal in position space, which makes them easy. That's how we proposed doing them back then, although in what I'm about to tell you, we're going to do it in momentum space because it's easier to put error bounds on that. And the important bit here is that there are no potential energy surfaces. You're doing dynamics directly using the particles that are moving and their fundamental interactions. So there's no electronic structure that you need to do first to then to parameterize the surfaces. And like I said, this is going to be done on grids and also called first quantization. So in second quantization, which is a normal representation for doing electronic structure, I might have an electronic function, the wave function that's a bunch of zeros and ones. So I might have the electron is in the pz orbital, so it's represented as 0, 0, 1. And I need to translate that to put it on my quantum computer as into a wave function on a grid that looks like a p orbital. Okay? And for electrons, that's reasonably straightforward. Where it gets trickier is with nuclear wave functions. And in really, this is the main technical contribution in this paper. Suppose I have a molecule that has 2 different modes, a symmetric stretch and a bending stretch, and I want to say I have 1 quantum of excitation in the first one, but nothing in the second one. The wave function of that, these are harmonic oscillator eigenstates of that Hamiltonian. And so in the direction of Q1, it's the first excited state. In the direction of the other one, it's the ground state. So it's a Gaussian, and in this case, it's a Gaussian by the Hermite polynomials. You've learned all of that in first year quantum. And these are the normal modes. And we want to convert those into the positions of the nuclei in real space, because the dynamics is going to be happening in real space, not in the space of normal modes. So that involves basis change, which on classical computers is very easy, but this becomes a tricky part on quantum computers. You need to do a rescaling of the normal modes. That's easy. But you also need to do an orthogonal transformation to rotate them. And then you do a shift, which that's the easy bit. So I'll have more to say about this in a second. But when I say that this is a wave function on a grid, what I mean is, for example, that if I have a one-dimensional grid, I have n qubits to represent 2 to the n lattice points. So the leftmost one is 0, 0, 0, then it's 0, 0, 0, 1, 0, 0, 0, 1, 0, and so on, all the way to 1, 1, 1, 1, with some amplitudes between them. And so this is a 2-dimensional plot of a wave function like that. And so the steps of the algorithm are again very similar to what I said. It's just initial preparation, time evolution, and measurement. Here it gets a little bit more complicated because the question is, how do you, what is the initial state? So we need to think about how do we prepare a pz orbital. And so we need to do some classical pre-processing to say, okay, the initial state is this electronic state of the molecule excited. So this is the initial state preparation unitary. At that point, we prepare the initial state in, for example, position space. It looks like this. We can then transform it into momentum space with a Fourier transform, so it looks like this. Then we do time propagation under the full Coulomb Hamiltonian. There's some final state after that. And then depending on what kind of measurement we want to do, we need to transform into the basis of the measurement operator. In many cases of chemical interest, that'll again be a quantum Fourier transform, so you move it into the position basis. So from the momentum basis back into the position basis, and then you do some measurement, which tells you, okay, at the end, the nuclei are here, or they're here, and the electrons where they are. Okay, so for state preparation, the idea is that we'll do very often in photochemistry, the initial state is not the hard bit. The initial state is some, the ground state of the molecule, which has then been excited. So it's not that the state preparation is the classically difficult bit. So you might say, okay, well, this is, I do Hartree-Fock or full CI or whatever on my molecule, and then I excite it to some excited state, but I have a representation of that molecule in terms of molecular orbitals for the electrons and in terms of the single modals for the nuclear configuration. So these are the Hermite polynomials, Hermite Gaussians on the nuclear coordinates. Both of these end up being projected into a plane wave basis and encoded as a matrix product state using the procedure that Bill developed for electronic states, and we adapted it to include also nuclear configurations. So the idea is that the totally generic molecular wave function is some mixture of configuration or superposition of configurations of products of electronic and nuclear states. Each of the electronic states is a Slater determinant. Each of the nuclear states is a Hartree product of single modals. Each molecular orbital is a product of Gaussians in the normal way. Each of the nuclear wave functions is a superposition of Hermite Gaussians, and the point is that you have all of these coefficients at the bottom, and then we have a recipe for stitching them all together to prepare an arbitrary initial state. The hard bit, like I said, there is this transformation from normal modes in which the input is given to you from a classical precalculation to position coordinates. This involves both a mass weighting of the normal coordinates, but also this orthogonal transformation from the normal modes into position space. And this involves change. So if you have a superposition like this initially of amplitudes on a grid, I need to change, the amplitudes stay the same, but I need to change the positions of the grid. So it's not just applying a unitary, you're actually changing what's happening inside the wave functions. And so this ends up being tricky. You do a QR decomposition to represent it in terms of diagonal operators and shears, and then you have a Givens decomposition that any orthogonal matrix can be decomposed into a product of two-dimensional shears, of generic shears, and each shear can be decomposed into a product of two-dimensional shears. And Bauer and colleagues a few years ago developed a reversible circuit for implementing shears. The problem is that this is tricky because you're doing it on a grid. So when you do a shear on a grid, you end up with errors because the points don't quite line up with the new grid, so you need to calculate those errors. You also get problems because when you shear, you can end up outside your original box. So you need to pad the grid to make sure you're not looping around. And this turns out to contribute substantially to the cost. So you have to be extremely careful about this. So that's the initial state preparation. We can prepare whatever state we want, and then we evolve it in time. And this is more standard. And again, the Google group, we've adapted their approach in doing this, although kind of adapted it to this specific setting. The idea is that we express the molecular Hamiltonian as a linear combination of unitaries. We construct a block encoding of H. So here's H in a unitary divided by its block encoding norm. And then it's quantum signal processes on this walk operator, which includes the block encoding. And the question really, in terms of the cost, is for the time evolution, is how many repetitions of this do you need? And this is the asymptotically optimal cost for that. And then when you get to the measurement, well, you can measure whatever you want in principle. The example that we give is the measurement of reaction yields. So if I have a molecule here, light comes in, and I want to know, for example, whether this bond is going to break, whether nothing's going to happen, or whether this bond is going to break. And what that means is that that's determined by the positions of the nuclei in space. So here's the separation, the distance from the oxygen to the carbon, and the distance between the bromine and the oxygen. And if I just measure the positions at the end, I'm going to get a single dot somewhere in this two-dimensional space, and I can I can construct transition state dividing surfaces which tell me which side I'm on. And so this is reasonably straightforward too. Okay, so I've got one more minute. The point is that we can do this is horrific, the paper is very long, but you can calculate all of the, everything down to gates. The take-home message is that it's efficient. So this is the final cost. It's polynomial in the number of particles, electrons and nuclei, linear in the time, and polynomial in the final error. And these are the gate counts for a number of problems which are all classically difficult. These could not be counted. These are the photodissociation problems of molecules that are important in the atmosphere. These are pollutants which are dissociated by light. And they differ in the number of particles you have, the box size that you need, the grid spacing that you need, and so on. But the upshot is that you need a few thousand qubits, and the total number of gates is 10 to the 13 or more. But that sounds kind of like a lot, and it is. This is a plot I've stolen from. It is, but I'm optimistic about it. So this is a plot of what's happened with FOMOCO over the past 6 or 7 years. Back in 2018, the expectation was it would take 10 to the 14 Toffoli gates, and it has come down dramatically since. We're sort of starting at the same place, and I really expect a similar kind of decrease because the gate estimation hasn't been fully optimized, right? So these are not absolutely tight error bounds. We made some approximations that could be significantly improved. Some of the stuff about, for example, the basis change, I can see a lot of room for improvement. And also some of the numbers that we chose for the grid spacings we don't really know what it should be. In practice, you would actually do it and see how it turns out. Okay, so hopefully I've convinced you that chemical dynamics is a hugely promising application for quantum simulation in addition to electronic structure, and I've tried to give you two approaches. One is an analog mixed-qubit boson approach, which uses trapped ions as a terrific platform. There's a million or even billion-fold reduction in resources, and this increases with system size. And we can use noise as a resource. So I think in terms of where is the quantum advantage, I think it's probably there in the near term. And then the digital approach is end-to-end and bounded, and it has controllable errors. And I think there's still a large scope of algorithmic improvement to bring these costs down. Thank you.
Sets up. Sorry, we cannot set up. If anyone has a quick question, and there'll be plenty of time for questions in the sessions afterwards.
So you do a lot of transformations of the reaction coordinates here.
Yes.
The ultimate thing you want to measure is there a configuration in this particular region or that particular
Yes.
region? So do you worry that your transformations could impose a cost? Could impose a cost because the Jacobian of the transformation could squeeze down the region that you're interested in too small?
No. And the reason is that the initial, the transformation, you need to do it initially. So you're given some initial nuclear state, and you need to transform it into the position of the nuclei initially. And there are bounds on how big that Jacobian can be. And then as time goes on, then you really only care about like where, then there's no more Jacobian. It's like, okay, are the nuclei here or are they where?
Thank you.
Okay, thank you very much. So now we have Torin Cettino, who's going to talk about quantum simulation of spectroscopy, algorithms, and applications.
Yeah, all right, great, thank you.